All right, we started the recording. All right, so by my clock, it's 1300 hours coordinated universal time. Time for the meeting to start. Welcome, everyone. For me, it's 8 in the morning. I know for a number of people on, it's Central European Summer Time. See that you're in the middle afternoon, and I'm sure we have some people on in the evening. Welcome to the joint Measurement and Analysis for Protocols Research Group and Measurement and Analysis Tools Working Group meeting. I'm Dave Plonka. I chair with Miria Kulwin the MAPRG group in the IETF. And our co-chair for this meeting is Nina Bergeson. And she can introduce herself in a minute when we switch to her portion of the content. But she co-chairs with our colleague Brian Trammell the Measurement Analysis Tools Working Group for the RIPE Regional Internet Registry. We have a 2.5 hour session scheduled today. I think we have a little less content than that, so we should be pretty comfortable in terms of timings. This is our recording notice. The meeting is being recorded now, and all the presentations will be. It'll be available on the IETF YouTube channel, and as usual for MAPRG, after the meeting, I'll post individual links to each of the talks on the MAPRG wiki, which is available through the MAPRG page linked here. Someone has their audio on. If you could please mute it, that would be helpful. Administrivia for today, the charters for these respective groups are at these URLs. This is the first time we've tried this experiment of a combined MAPRG meeting with RIPE MATWG. And the idea was that if we did it outside the IETF meeting schedule, then maybe more people could join between the two when both of our groups have been having a bit of trouble scheduling in the pandemic era. Both the groups have mailing lists that are mentioned there that you can subscribe to, where, for instance, you would have heard about this meeting being scheduled. Today's slides can be found at that URL there. And of course, all you've already know, but the WebEx link is available in the agenda and in these slides at that URL. So Nina, why don't I pass it to you and you could introduce yourself and tell the folks about the first part of the agenda.
Thank you. Do you hear me?
Yes.
Yeah, great. Thank you. So I'm Nina Bergeson. I co-chair the RIPE working group on measurements, analysis, and tools, along with Brian Trammell, who's also on the call today.
Hello.
Today we're going to talk about. So basically, the working group mostly focuses on measurements and on tooling, and a lot of the time we also focus on RIPE Atlas system. Today we're going to talk about the mechanisms and performance evaluations of the RIPE PMAP tip geolocations. Massimo is going to talk. And then we will have some measurements about what happened under the pandemic that we're still running through. But so far, and we have Vesna and Lai is going to give us their observations on that. We also thought that we would have a tools update from the RIPE NCC. People, please be mindful of muting their microphones. Thank you. But unfortunately, we had to cancel the tools update, and we will just have to show up at the next RIPE meeting to get the latest news on the Atlas and other tools from the RIPE NCC. But happy to be here, and I'm really excited about this joint meeting. This is my first IETF related meeting. Ooh.
All right. Well, okay. Welcome, Nina, and thank you for that overview. So following the portion that Nina will be running with the items that she just enumerated that were organized by Matt, we'll switch to the MAPRG meeting proper, and MAPRG is in the IRTF, and so we have an intellectual property rights statement that binds you to, as a presenter, if you have intellectual property regarding it, you should disclose that, just the CAN portion. So this will be an official MAPRG meeting as well. And this applies only to the MAPRG portion of the meeting. So the second part of the agenda that Miria was wonderfully helpful in putting together here are the following. We'll have a presentation about measuring and analyzing the RFCs themselves, the security sections, the sort of a meta-analysis by Mark McFadden. Then we'll switch to Jake Holland talking about latency and AQM observations on the internet. Then Philip Brun on packet latencies in mobile networks. Mike Kosek is with us to talk about their paper and from an academic conference, must, should, don't care, TCP conformance in the wild. And then we'll switch it to, it's the last session portion of the session, to Stephen Stroh's talking about deboganizing this /12 prefix that the RIPE NCC is now using. Before we switch to some advertisements for various projects, I'll talk a little bit about how we're going to run the meeting. For each of the presenters, I'll switch you, to the best of my ability, to you being the host in the meeting, which will allow you to show your slides. If you have any trouble with that, no problem, let me know, and I'll show them like I'm going to do for Mark's presentation. For those participants that have questions, please use the chat icon, which usually shows as a round circle on your WebEx window, and you can chat to everyone. Just type +Q, and that will create a queue of people that we will invite you to ask a question by unmuting yourself and doing so. If you'd rather the chairs ask it or someone else ask it on your behalf, just type the question in that chat box to everyone so that we can see it. And we'll have some time between each of the presentations to visit those questions there. MAPRG invites projects that are not presenting at the meeting to also give us advertising slides for their projects. And for this meeting, Miri and I created a couple because we have not met so far this year because of the pandemic and scheduling issues between IETF 107 and 108. This is our first meeting of the year. So let's bring you up to date on some of the content that we would usually have hosted in MAPRG. IMC, one of the preeminent measurement conferences, took place last year in October, and PAM 2020 in March of this year, and that's on either side of the beginning of the pandemic and lockdowns for most of us. So what we want to do is remind you here of a couple of papers. For instance, Giovanni offered these as potential papers to present here, but we decided not to because they'd been presented at MAP meetings prior. But the IMC content is up with the links to the papers and to videos. And I'm happy to say that also Pam did a nice job of recording the videos and also making, I think, registration free for that event when it happened. So you can check either of those URLs to see these papers and the others from those two conferences. Another one of the preeminent measurement conferences was TMA that was held in June of this year. Similarly, TMA has had recordings or videos of the papers, and those papers are up at that URL. And Gareth, one of the chairs, has created a YouTube playlist at that URL for the subset of papers where the presenters gave permission to share the video. So check those out. Lastly, Anna Brumstrom has offered to us this advertisement for a project with she and her co-authors, where they studied narrowband IoT, Internet of Things devices into major metropolitan areas, and my understanding is their interactions, for instance, with LTE and cellular in that area. And we included them here, although they're not involving specifically an IETF protocol. That they've released a data set, so it could be the basis for other people to do research. And Anna's provided a link to the paper on archive as presumably a preprint version of the paper. So give that a look if you're interested in that technology. So now I'm going to hand it back to Nina, and she's going to walk us through those first set of presenters. So coming up Let me stop sharing this screen.
Yes, thank you so much, Dave. That was a really interesting.
I just need to know who I need to make the presenter next. Let's see.
Next, we want to
Massimo.
invite Massimo. So if you can make Massimo the co-host, and we would like him to share his screen and give his presentation.
Yes.
Okay, Massimo, you should be the presenter now.
Perfect. Thank you very much. So are you able to see my slides?
Yes.
Perfect. So hello, everybody. So my name is Massimo Candela. I'm a senior software engineer at NTT. First of all, I would like to thank the organizers of this event because I personally really missed the MAT working group at the last RIPE meeting. So I'm really happy that we could do it here. So the presentation here today, I will show you a mechanism behind this service called RIPE IP map, and also I will show you a performance evaluation we did it together with the colleagues from CADA. This is a paper that appeared in the issue of April 2020 of Computer Communication Review. And well, let's start from the beginning. The first thing is, what is this RIPE IP map? So RIPE IP map is a service that has been developed and is offered by RIPE NCC. And it is essentially a service that you provide an IP address and will try to tell you where such IP address is geolocated. And so a bit of history behind this service. The first attempt to tackle the geolocation topic was presented in 2013 by Emil. And essentially introduced the Open IP map platform, where you can use crowdsourced data to improve IP geolocation. And in 2017, in another RIPE meeting, I introduced instead RIPE IP map, which is the idea behind that is a system that has the possibility to run various geolocation approaches and offer this platform to people that they want to provide a new geolocation system. So each geolocation approach runs in an isolated fashion in something called geolocation engine that you can see in this chart at the bottom. And they produce some sort of geolocation in a unified output format, and after they pass through a reducer step, and the final answer is computed for the user. So each geolocation engine can do some stuff, and for example, one of these is the crowdsourced data, and another one can do active geolocation. And in particular, we are interested in one of the engines doing active geolocation. And in this presentation, we will study the single radius engine. So a bit more of information. I developed the single radius engine while I was a RIPE NCC and not anymore RIPE NCC staff, but we got some feedback that the system it works, and there is also a paper that reports on a country accuracy of 99.58 for their use case. But we needed a formal study dedicated to in particular to single radius, and in particular also to city level geolocation, and also the mechanism behind was not for single was not formally described anywhere. So at some point, CADA decides to study single radius, and the guy that you see here in the picture is Ben, that he presented at RACI first preliminary results. The study was black box, so at some point they decided to call me and on board of the team to essentially provide more insight on how is working behind the scene, the system. That's how I'm involved in this research project. So just to start with what is active geolocation? Well, simply like you want to geolocate an IP address, and to do that, you take a host that you know the location of, and you do a ping measurement to the target. In our case, the host is, for example, RIPE Atlas probes. And after you do a ping measurement, you know the latency, you get a latency, you transform it in a distance with a coefficient factor usually expressed in kilometers per millisecond. We will see it better later. And what you know is that the target IP is going to be around a specific area around your source of the measurement. So like in this case, the circle. So single radius also, as the name says, does exactly this, plus some additional steps. So the first thing is there is an initial selection of the probes. This is an important step because a lot of methodologies, a lot of models describe, they assume the possibility to select all the probes possible, but maybe are based on platforms that they have a couple of hundred probes, or anyway, they are developed not as a production service. And the main issue you have is that you cannot really select in a serious platform like RIPE Atlas, you cannot select like 10,000 probes for geolocating one single IP, because you will do essentially a DDoS every time. You would trigger a lot of ICMP rate limiting. You would just also stress the platform itself. So there is an initial step that we will see for the selection. After you have the probes, you do the ping measurements to the target. You select, at least single radius does that. You select the closest, the fastest of this ping measurement. And it has to be also the round trip time below 10 milliseconds. We will also see a bit better what this threshold is. And after you take this round trip time and you convert in distance by doing round trip time divided by 2, multiply for 2/3 of the speed of light. So the round trip time divided by 2 is the usual approximation that it's done to calculate the one-way delay, or at least, as I said, an approximation of it. And the 2/3 speed of light is the upper bound of the signal traveling in fiber, which assumes that between the source and the target, there is a straight fiber with no hop in between. And so they are really big approximation. The last step is that single radius does, tries to bring a bit more accuracy to the process, is to select inside that circle, inside that area, 100 cities, if there are at least 100, and it ranks them based on distance from the source, number of facilities, and population, because the main goal of RIPE IP map is to geolocate infrastructure. So these parameters, they kind of give an indication of how much internet infrastructure there is in such cities. All of this methodology is described better in the article, but I briefly show you just one detail, is the initial probe selection. Essentially, the goal here is that you don't know where the target is, but you can select probes that they are topologically close, hoping that they are also geographically close. At least that's the idea. And to do that, you can always do the target IP, convert it to autonomous system with IP2S lookup, and use BGP topologies to infer the topology and try to select probes nearby. So one thing that the single radius does is selects BGP neighbors, distance 1. And another thing that it does is it uses peering DB information to detect which IXPs the autonomous system of the target is doing peering. So you detect the cities. This is an idea that initially introduced by Vasilius that you probably all know. And so at the end, what you do is to have a set of cities and a set of autonomous system, and you select, you ask RIPE Atlas to select probes nearby, which sometimes it works. You detect the geolocation with one single probe. Sometimes you need up to 500, which is the upper limit, but it's still anyway better than selecting all of them or select random. So this was the rest, as you saw, is essentially basic basic active geolocation. More details are in the article, but more or less we cover everything. So I'm going now to the part related to the evaluation. We evaluated the accuracy compared with Maxmind and NetAcuity, which are the leaders in this field. We evaluated the effectiveness of the probe selection method that I showed before. We evaluated the coverage. We evaluated also the router level consistency, where essentially we ask a single radius to geolocate IP addresses belonging to the same router and checking if we got the same essentially geolocation. And overall, the goal is to provide suggestions to REP and CCA to the entire community. The one in bold are the points that I'm going to describe now. So the first thing is we need two datasets. One is for the ground truth dataset is essentially a collection of IP addresses of known location, and we need this to validate the accuracy. We use the ARC nodes, the NL-NOG ring nodes, the MLab pods, and the ARC proximity dataset. In this table, you can see the division of IPs by region and also coverage in terms of unique autonomous systems. And after we filter out the IPs that they had wrong metadata or they were offline, so not possible to do geolocation, and we reported some cases of wrong or missed or corrupted metadata to the administrators of this platform. So this was also one of the benefit of this exercise. So in the end, we had 968 IPs, and for the coverage dataset, where we are not interested in having information about the geolocation itself, but we need some responsive IP addresses, we use the MANIC interconnection dataset produced by CADA, which has more than 16,000 IP addresses active and answering pings. So go straight to the accuracy results. You see this CDF. The blue line is single radius. The orange one is net acuity. The green is max mined. And you see on the x-axis the error in the geolocation in kilometers. So we consider a distance below 40 kilometers accurate at city level, a distance above 40 kilometers not anymore accurate at city level. This 40 kilometer is a threshold that is has been used multiple times in literature, and it's considered kind of average metropolitan area size. And we can see that single radius outperforms the other two platforms and reaches an accuracy that is 80.3%. But the comparison is not yet finished, because if we compare the median 75th percentile and the 95th percentile of the three platforms, we see that, for example, for single radius is 6, 26, and 344 kilometers of error, while for net acuity is 10, 80, and almost 3,000, and for max mine is 17, 278, and almost 3,000 also. So single radius, even when produce an answer that has an error above the 40 kilometers, so not anymore accurate at city level for our parameter, produces anyway an error that is considerably much smaller, like 300 kilometers compared to almost 3,000. But the problem, okay, before to go to the 10 milliseconds threshold that we said before, we analyzed how it would change, because the threshold is essentially used in various works, and the idea behind it is that if you have active measurement above 10 milliseconds, the kilometers are so much that it's not even worth to try to give a guessing of the geolocation. That's the idea. But we try to investigate what would happen if we would use geolocation different threshold, like from 1 to 10 milliseconds. And in particular here, I show the picture with 2 milliseconds, we have the 95th percentile of city level accuracy. Of course, now the main problem of active geolocation compared to the other systems is that there is only a finite amount of answer you can give. So active geolocation usually is not so good in terms of coverage compared to the other platform, because the other platform can essentially provide an answer, whatever it is, to whatever question you have. But with active geolocation, only some IPs are reachable, or only some IPs are inside a certain boundaries of distance. So we use the MANIC dataset to geolocate, and we find an answer for 78.5% of the 16,000 IPs that were there. And so this is actually a good result in terms of numbers. And we also went to analyze, like we did before, what would happen if we would make it more accurate. So if we would change that threshold. So if you reduce the threshold from 10 to 5 milliseconds, we dropped the coverage to 51.1%. But if we go to 2 milliseconds, where we would have a 95th percentile accuracy at city level, we have a coverage of only 24. So you do your math if it's, you can do your tuning if it's convenient for you or not. In my opinion, you basically drop, you increase a 15% accuracy, but you lose a 55% coverage. So I'm not sure how much it is worth in our case. So this is basically the only part that I want to show for today. But before to close, I want to just give some words about, I think it's always important to realize. Yeah, it's always important to realize that every analysis that you do related to platforms like the one that we saw before and related also to geolocation of hosts, they have an intrinsic bias induced by the fact that the internet infrastructure is not distributed equally in the world. So in our research, we do also drill down for various regions, and we try to split the various results. You see here instead just the global view for simplicity. Also, the ground truth dataset of the IPs is really hard to obtain such accurate set of IPs that you can test and that you know exactly location. So this is also, I mean, we had 968, which is a big amount compared to a lot of other works, but still a small amount compared to the entire address space. So I want to thank the colleagues from CADA, which are listed here for the hard work and the collaboration that we did. And also, this is my last slide. And if you have questions, this is the moment. I have also here my contact, so you can also contact me offline if you would like. Thank you very much.
Thank you for that, Massimo. And we do have Jay Ignacio in the queue with a question. So please unmute yourself and ask her.
Yes. Hi, everybody. I would like to ask to Massimo how many times you need to get the location. And I have a second question is how many pings you need to send for every probe to the location, the IP that you want to locate it. Thank you.
So I didn't get the first question. What, so the second one, I got it. What was the first question? Sorry.
How many times? Because you have an IP, you run this system, and you spend some time to run the system because to send the measurement to the right atlas platform, you get times, it's not immediately. So just to have an idea how many times involves the full measurement for one IP.
Yeah, perfect. So so to the amount of time the system takes to geolocate, it is set on average about 3 minutes. So after 3 minutes, the API allows you to retrieve the data from Atlas and do the query. So if you look at the measurement itself, it could be faster, but we don't want to, since Arrive Atlas has a queuing mechanism for the measurement, we don't want to retrieve data too early and give a wrong answer. So we wait the 3 minutes that we calculated as basically the maximum time for a measurement to be a one-off measurement to be executed. So that the answer is in general 3 minutes, but the once an IP is of course calculated, the answer is cached, so it will take milliseconds to just retrieve it again. This is the first answer. For the second question, so how many ping measurements? That depends on the amount of probes that were selected. So the probe selection mechanism can basically has a priority queue of measurements to probes to select based on the topology. So we can select one, but it can select up to 500, and after basically you have a usual ping with 3 attempts to geolocate the target. So that depends on the probe selected.
Yes, but imagine that you get 100. You got 100 pings, or every probe you send most, you send 3 pings, or this is my.
It should be for okay. So no, it is a one-off. So we send one-off, but each ping has 3 attempts, so 3 run-through time attempts.
Okay. Okay. Thank you.
Thank you thank you very much. So the next question we have is from Daniel Karenbach, and he asked in the chat, did you outline, did you not mention the suggestions that you had to the RIPE NCC, and what were they?
No, the suggestion were like the experiment overall that we had for the use of different thresholds. We did a good amount of. We have also a list of them. They are more explicit in the article. So we did various things, among which the graph that you see here can be used by the user to essentially tune their own. The API provides the round-trip time used as a threshold, so you can use this to provide your own score. That is one of the suggestions. The other suggestion that I have for RIPE NCC would be to at some point implement a mechanism with multilateration. We did some preliminary tests by using for example, regional coefficients to transform to distances, and the results were extremely positive in terms also of reduction of ambiguity of the geolocation. But that would work with a multilateration approach. And another one could be experimented is with the removing the last mile latency from the measurement to improve the accuracy. So this is the overall, I would say, high-level summary of it. And the material is public, and I will make sure that all detailed suggestions are delivered. By the way, this research ended up also with some patches that we did to the IPMAP source code itself, so after the analysis.
Great, thank you so much, Massimo. That was really interesting. If you please stop sharing your screen.
So thank you very much. Stop sharing.
Excellent, thank you. And then we would like to invite Vesna to share your screen and do your presentation about the observations during the pandemic.
And okay, and I just switched Vesna to be the presenter, so she should be able to do that now.
Excellent, thank you.
Hi, everyone. My name is Vesna. I'm from the RIPE NCC. I'm a community builder, and I am giving this presentation on behalf of my colleagues, mainly Emil Aben, who couldn't be here, but these are his slides mostly. So we have been active in analyzing the data from the RIPE NCC measurement projects and publishing our findings on RIPE Labs. We have a collection on /COVID-19, and you can find all these results that I'm going to talk about there. So from the beginning, other operators also contributed to this and also published some of their findings on RIPE Labs. And we tried to move our real hackathon that we wanted to have to the virtual world, and that worked more or less as much as possible. So we also published some of the results of that hackathon there and some of the recommendations for the security regarding COVID, mostly the applications for the tracking and so on. So you can find more of information about our events also on RIPE Labs. we have basically two types of results. One is about the network stability based on the routing data that we collect, and the other one is about network delays. So the first one is based on so-called RIS, or the Routing Information Service. And if you're not familiar with that, it is a little bit like the route views. And I'm a bit sad to actually compare it to the other one, which is a competitor, but it's more well known, I guess, and it has a better name, I must admit. So our service called RIS is having a global view of the BGP. And so we have the routing collectors that are listening to the routing updates, and we can show you either the history of the routing changes, or you can get the direct updates as they happen. So there are multiple ways to access this data. And basically, this is an invitation for the other researchers and the network operators to use this data, because it's open and it's very well documented how you can use it. So normally what you would use that for is to kind of troubleshoot your network and to show how is your the WISP performance actually different from what is happening in the world, and maybe also to help you kind of combat some of the route hijacks and takeovers. And all of that you can do by your own analysis, or you can see our views on the stat.ripe.net. So when we looked at the COVID impact on the global BGP, we thought, well, it's going to flare up because people can't travel to their distant points of presence to actually do the maintenance. And there was the restricted access to data centers. So we thought, oh, now this is going to actually explode. But we were wrong. So basically, internet is stable, at least on the routing level. So this is the global view over time, and you can see that from November until July, so November last year until July this year, there weren't many changes. So the other way to look at it is by the type of the announcement. So either by adding the prefixes or removing the prefixes, or the origin changes. Again, there were some flares, but it was nothing systematic, and actually it didn't coincide too much with the lockdowns per country or anything, because you could see that in December previous years, actually there were similar events. So our conclusions are that the pandemic didn't impact the internet on the global routing table level. So as usual, we can see these weekly patterns. And so apparently all the operators are working very hard to maintain the internet now, when it became even more important for even more people who are working remotely and schooling remotely. So if you want more details, they are on RIPE Labs, and I do invite you to actually analyze it on a more granular level, and to compare it with your own experiences and maybe come up with different conclusions. And then the other type is measure network delays by using RIPE Atlas. We worked with a researcher, Roma, who made a very detailed analysis, and then he published that again on RIPE Labs. So this one actually is how can I call it, like a dashboard where you can choose a country, and then we have pre-coded some dates of the very clear lockdown times per country, and then looked at the month before and at that time the month after the lockdown to compare. But now you can also get the latest data. And so this is just a very quick overview per country. And again, you can put your own country when analyzing data in your own way, or a different time period. And so per country, we also show per a specific provider what were the changes in latency. This is based on the RIPE Atlas data, so the pings, the ping measurements. And so this is the RTT that you can see here. And again, there are some spikes for some providers, but for us looking from a distance, we couldn't really see a very clear reason why something would happen, but the people from a specific country probably can actually analyze it more related to their political situation or the lockdown details and so on. And so the other example is a little bit more busy when you just look at it as a picture, as an illustration. And so there are much clearer differences from before the lockdown, during, and what is the situation now when the providers have actually increased maybe their capacity or found a way to deal with the increased load. So there are conclusions to be drawn here, but we didn't go into the very specific details ourselves. This is more to show what is possible and to give like a very quick overview per country. How does RIPE Atlas see the networks and how they are impacted with the heightened usage? So the good news is internet is doing fine. And if you would like to explore it yourself, here are the links to the interface and to the projects that I mentioned. So this is something that I added since I've sent the slides. This is not in the slides that I uploaded, so pay very close attention. We also opened some weeks ago a community projects fund call for suggestions. So RIPE NCC is decided some years ago to start funding the projects that are for the good of the internet. So the main criteria is that they are based on the open source and the open data. And so the projects that contribute to the resilience or sustainability of the internet can receive money. And we have already highlighted some of the winners from the previous project fund on the RIPE Labs. And for this year, you still have a few days, few weeks to apply. So please approach your communities and spread the news, because we would like to support the existing projects or the new ideas that work on the good of the internet. Contact us if you have any questions. There are my email addresses, Emil's, and a lot of Twitter details and RIPE Labs. Thank you very much.
Thank you so much, Meshna. And we have a couple of questions. So first, I'd like to invite Jay Ignacio again. Please make sure.
Yes, hi. Thank you. Thanks for the presentation. I have been doing also measurements in Latin America using RIPE Atlas. Here the problem is we have a few groups among 400 spread in Latin America. Some countries have very few and so on. But we try to identify, we concentrate in Argentina, I am from Argentina, to identify the path, the routes through the CDNs, just to most used CDNs, which are where dominates the traffic into internet. And after that, we performed some measurements, basically trace route, because we wanted to analyze the traffic inside different parts of the network. We just see the results, not so much analyzed for the moment, because we need people to do that. And it's a little busy moment at that time, because the pandemic makes so complicate everything. But the first results are that in some specific time you got some congestion in some IXP, not exactly into the IXP, but in the some specific.
I'm sorry.
Yes, sorry. Okay, I just finished but
Yeah.
for the problem is perhaps you need to analyze the or perhaps it's possible to analyze the information deeper. And if you want, I can send an email with the details. Thank you.
Yes, I would be interested. And if you publish something, we can republish that on RIPE Labs and promote it in our community. And then maybe you can get somebody to cooperate with you and help you out. And another comment on this is in the regions where we have fewer probes, it might be possible to install the so-called software probes. I have posted a link in the chat, and that's just easier from the logistics point of view. So please consider that.
Yes, thank you. Very good idea.
Thank you so much. And the next one we have is Dave.
Yes.
Dave, take it away.
Thanks, Vesna. I noticed in a couple of your slides you had, for instance, details like 18th of March, Belgium went on lockdown. I was wondering what do you have as a resource in terms of a journal, or what advice do you have for the rest of us that might want to study this on how to find real world events about when those lockdowns happened, and also presumably the challenge is going to get even worse as we get more and more waves and changes with lockdowns. What have you found?
Yes, so this was the first attempt to work on this, and it was quite early in the and when we were hopeful that there will be one lockdown, one date per country, and then later on we realized like, oh, that was not so obvious. So the first thing is that we actually consulted the Wikipedia page, which lists per country when was the lockdown date, like a third-party neutral resource. And then currently there is an idea, or at least this is my wish, to change this to make it into a monthly report, so that we just look at a fixed date in a month per country, and then we can see what the changes are regardless of the actual lockdown date, because it's going to become fuzzy anyway with the new lockdowns and the second waves and N+1 waves.
I see. And the Wikipedia page was specifically about the overall COVID-19 pandemic?
Yes, it is listed in that article by Romain, where we have looked up the dates, but he had to actually hard code those dates per country, and that's a lot of manual work. So I think if we were to automate this to the next level, it should just be easier than that.
Okay, thank you.
Unless somebody has a better idea, so we can work on this later on online, but not on this WebEx.
Right.
Great. Thank you so much. Thank you, Vesna. That was really cool. Next, I'd like to invite Lai. Lai, I hope that's the correct pronunciation of your name.
Hi.
Lai, thank you very much.
Give me a minute to make Lai the presenter, and there you are. Okay, you should be ready.
You're presenting now, and you can share your slides.
Great. And we can see them?
Yes.
Okay, great. So hi, my name is Lai Olson. I'm the project director of Measurement Lab. Thanks for having us. Similar to Vesna, I'm here to just share the fact that our data exists and give an overview of how it's generated so that researchers here can take it and run with it. So talking about what is MLab, just to speak briefly about the goals of our project. Some of you may be already familiar, so apologies if so, but for those of you who haven't been introduced, our mission is to measure the internet, save the data, and make it universally accessible and useful. I am preaching to the choir that there are many ways to do this, and by no means do we claim to do all of them, but we do focus on principles of openness and transparency. So all of our data is open and free to access, and I'll talk more about how that works. I always think it's useful to, when talking about Measurement Lab as a project, to think about the problems that it was trying to solve. The project was started in 2008, so it's been around for 12 years. And it was responding to a widely reported problem of not having access to commercially maintained servers that were widely deployed enough with ample connectivity to support the kind of experiments that internet researchers wanted to perform. And then another issue that it's trying to solve is the issue of big data sets and being able to share the data that these experiments are producing. So these are the two kind of problem sets that the project set out to solve. And then if you fast forward 12 years, we have a platform that I'll talk more about, a pipeline that archives all of the data that the platform, that the experiments generate, and then the data itself that we make publicly available. We also maintain a suite of tools that are focused on community-based data collection. And we, of course, also try and foster a community, much like RIPE, to get researchers involved in using our data. Our team is based at Code for Science and Society, which is an open data and open science fiscal sponsor. We also have Google as a core contributor, and one of the things they do to contribute is they donate the time of a team of software engineers. So our team is made up of 2 organizations of core contributors. So getting into the nitty-gritty of how the platform works, just to give a sense, currently we host about 500 or so servers in 60 plus metro areas and off-net service providers. And for us, off-net we define as tier 1 data centers where they're serving more content than people, so essentially outside of access networks. On these servers, we host measurement services, and they're basically the server-side code. Then clients are developed to run tests against them. So we see this as measuring the part of the internet, going past the eyeball network, so to speak, and having the clients test against servers that are within the backbone. Anyone can develop clients, so the server-side experiments are mostly written by academic researchers and approved by our experiment review committee, but anyone can write the client-side code. One example is the UNI application runs an NDT test, and we'll talk more about NDT. The Google search client as well is one of the integrators. So if you Google how fast is my internet, we are what pops up. Or in the NDT test that is hosted on MLab is what pops up. By nature of NDT being on the project the longest, we have the most data for that test or for that measurement service. And so often when you hear about MLab data, we're actually probably talking about NDT data. And for that reason, I'll talk about that a little bit more. These slides are kind of my standard slides, so I get into a lot of nuances here that actually maybe folks here are more familiar with than most. But to break it down just briefly, NDT, which is one of the measurement services that we host, is measuring the single stream performance of bulk transport capacity. Bulk transport capacity is trying to look at the reliability or the ability to deliver packets reliably across that link. Just have some notes here about how often this term is conflated with link capacity. I feel like this is the audience that understands the difference, but suffice to say, often both are conflated with speed. And so it's often thought of as a speed test. It's also measuring the single stream performance as a way to effectively measure the baseline of the bulk stream, or sorry, the bulk transport capacity. And put these together and you get NDT. And so a question that we often get from kind of end users is, why is my speed test different than other speed tests? And it's just an overview of what NDT specifically is trying to measure. And then in combination with our off-net platform, that's giving you a vantage point outside of the access network. This is these are the characteristics of the MLab data set, or more specifically the NDT data set. One thing to note is that NDT7, which we're actually in the process of migrating the majority of our clients to, supports BBR, so has a better ability to model the network that it's basing its congestion control off of. It also runs over TLS and uses modern WebSockets, and actually today we're releasing a blog post talking about the comparisons between NDT7 and NDT5, our previous protocol. And there's some links there too if you're wanting to know more about either BBR or NDT7. You can also run your own NDT server, just as a side note, if that's interesting to anyone. This is the same thing that we run on our CoffNet platform. You can run that same server-side code on any machine that uses Docker. These are more slides about our other measurement services that I encourage you to look at in the slides that I uploaded. But the main thing that I wanted to get at, if there's like one thing that I can communicate today, is that there is a ton of this data, and it has been being collected all through the pandemic and longer, for 12 years to be specific. And as of today, about 3 million new NDT measurements are added per day or produced per day. And as of 2020, we're close to 2 billion rows of NDT rows in our NDT table. Through the pandemic as well, more people are testing, more people are home, more people are trying to figure out what's going on with their connection. And we have been able to, I mean, you can see almost double the size of testing. This is just the US, but this has been a common behavior across countries. So there is more data than ever. And I think the takeaway here is that we really invite researchers to join us in analyzing it. And we don't have a research team, so we would love to work with you to support your research and your use of this data. Just going through some of the other slides. These are just getting at that it's all open and free, and I'll actually go on to the slides about accessing the data. So the most common way is through our visualization site. I'm not going to exit out of the presentation, but if you go to that site actually right now, there's Data Studio dashboards that make it really easy to just piece through what country you're interested in, as well as what city and ASN, and look at the data through the pandemic week by week. There's also, but the next most popular way of accessing the data, and probably for most folks here who are interested in looking at lower level metrics, is to use BigQuery, and that's just a sign up on our Discuss mailing list, and you get a login, and it's free to run queries as well. So if there's any questions on how to access that, we're always here at support@measurementlab.net to support your analysis. I think I'll just close by talking about just even outside of the COVID-19 pandemic, we're really interested in engaging with this group specifically, actually. So this is a really great opportunity to be introduced to you all, and I would defer to your expertise in terms of how we can be useful or how we can contribute to this working group. Some ideas, if you are part of a service provider, we'd be happy to talk to you about pod sponsorship for extending our platform. Also, as I think I mentioned a little bit, the platform, the experiments that run on it are approved by our experiment review committee, but we're open to any experiment that is open source. So if you have an experiment that would scale well on the MLab platform and benefit from using it, as well as generating open data, that's something we're really interested in talking about specifically with this group. And I think, again, the invitation is to please use the MLab data and let us know how we can make it more useful to you. And here are some examples actually of the researchers that have used it so far to analyze the COVID-19 impact. One is Roman, which Vesna talked about earlier, and then also a researcher with UNI who looked at the network performance in Italy. And so I'll pause there for questions or end there for questions.
Great, thank you, Lydie. We do not have any questions in the chat. There's a discussion about the previous presentation. And I wonder if that is something that we want to talk about now, or we want to push that to an offline discussion at some later point.
Should probably take that one offline.
Yeah, we're just about on
Looking at the
schedule right
clock.
now.
Yep.
Yeah.
So if I bet we might have some time before the meeting ends, which I'm happy to come back to it. Otherwise, we'll do it on the mailing list.
Great.
So I'm going to make myself up. Nina, I'm sorry. Are you done there?
I think we want to. I think we want to put Robert on the spot.
Exactly.
Yeah.
It
So we
turns
noticed
out-
that. Yeah. Good.
It actually turns out that Robert joined the meeting. So and then he found out that he was set to present. So kindly enough, he's gonna give us a small update on the current state of the RIPE NCC tools. So if you can please, Dave, make Robert Sturkey.
Sure,
Or
sure.
he's gonna do it verbally. So there will be no slides.
Yeah, I have no slides, so
Okay.
if you can hear me anyway, then I don't.
Yep, we
need
can
to
hear
be-
you. Yeah,
Okay.
just go ahead. Thanks, Robert.
Excellent. So yes, thank you very much for putting me on the spot here. But it's fine. I unfortunately will not have slides to show you what I'm talking about, but still probably I will try to be coherent. So this is the RIPE NCC tools update, and I usually begin with RIPE Atlas. It's still stable and it's still growing. We at the moment are floating around 10,000 results per second coming into the system. So that's a lot of result data from all over the world. We have about 11,000, a bit more than 11,000 end devices that we call probes. And we also have 650 RIPE Atlas anchors, which are somewhat bigger machines that you can also target if you want to measure something and you're looking for a target in the network. Now, this is a lot of data that we're collecting. So one of the feedback that we got recently, or I should say continuously, is that if you really want to work with all of that data, that's relatively hard. So what we are doing nowadays is putting all of that data, or almost all of that data, onto Google BigQuery, somewhat similarly than Measurement Lab does. And we plan to open that up to the whole world, to the research community in particular, so that you can get access. And with the BigQuery interface, you can really, really dig deep and very quickly into details if you want to. So that's ongoing, and I expect that we can make some announcements soon, probably or hopefully before the next writing. If not, then the one after, meaning everyone can have access to all of that data. This is in addition to the way we present and make our data available to the community anyway on the Labs platform. It's just making it easier for anyone to analyze that. As you may have heard from Vesna, we're working on what we call software probes. So these are basically software packages that you can deploy anywhere you want on your home router or your web server or your any kind of server that basically acts as a RIPE Atlas probe. It does exactly the same thing, except that you don't need to deploy the hardware itself. So in some situations, especially if hardware is difficult to ship to a target, this can come really handy. So Vesna posted the link, but it's relatively easy to find anyway. If you want to jump on, you can do this. We're still supporting the hardware probes, and we don't have any plans currently to stop supporting them. So don't worry, if you want to have a hardware probe, you can still apply for one and you will eventually get one. We are working on improving the actual measurement software. There are some new measurements coming up, and we're trying to improve the existing measurements. So it has been pointed out to us, for example, that the trace route measurements could be more efficient, which is on the agenda for us now. The VM anchors are still growing. We're doing some lifecycle replacements. As you can imagine, if you deploy hardware every now and then, you have to refresh that. And these are rack-mounted PCs, so every now and then that needs to be done. Somewhat interestingly, 10 years of RIPE Atlas is coming up. It's surprising even to me that we've been doing this for 10 years, but it's almost 10 years now. The exact date is October, end of October or mid-November, depending on which number you want to look at. So what you can expect is that we are going to do some small gimmicks, interesting tidbits of information, and some celebratory tweets and pages that we can put up. I think that for a measurement platform, 10 years is a lot, and I'm sure Measurement Lab is also in this ballpark. And also, if for this event you would like to appear and show us what you did with RIPE Atlas, so if you have something like a testimonial that you think is worth sharing with others, then please reach out to us on the usual channels, and we'll try to include you in the information that we will put out. Also, if you would like to sponsor Atlas, that's always possible. RIPE-Stat, that's one of the tools that has not been mentioned today just yet. So that's our resource explanation service. If you ask, what do you know about an AES number or an IP prefix or an address, then we will spit back a whole lot of information about geolocation, routing, DNS, and so on. This service receives more than 100 million queries a day, all of which require some number crunching on our end. So that's a challenge to keep up, but the team is luckily very agile on that one. So they are really trying to do their best to do this. The user interface will be revamped probably still this year, maybe early next year. So we will have something that's nicer and works better on the mobile platforms, which more and more people ask. So if you want to know something about an IP address on the road, you can do that very quickly. IP map, that has been mentioned both by Massimo and I think also by Vesna. Indeed, we're still working on that. And as Massimo mentioned, the system's point is to provide infrastructure geolocation information by combining multiple inputs to such a question, which we call engines. So the engines work independently. They make their own decisions about what they think that particular IP address is, and then the system presents a unified output of that. The engine that Massimo described is one of those, but we're still working on more of those to make it more useful for people. RIS has been mentioned by Vesna as well, so that's our routing information service. There is some internal thinking about what's next for RIS, and we really want to cooperate with people who actually want to cooperate with RIS as well. So both in terms of peering with RIS, providing data to the system, but also running route collectors if you're so inclined. That's one of the features that we would like to explore a bit more. One of the features that I would like to mention here is which is RIS Live, which is basically the streaming access to the RIS data set, which is real-time access to the data that we have. And Massimo, in his other working time, has been working on some alerting tools based on the RIS Live data. So if you're interested in real-time routing information and anomaly detection and so on, then I encourage you to check out RIS Live and the BGP alerter tool that Massimo has built. And in other news, we have an arm that does research within the RIPE NCC. Vesna mentioned a couple of examples, and one more is coming up at the end of this session. So that's measuring about 2A10/12 in the IPv6 space. But in general, if you want to be up to date about what kind of interesting information we found or are looking at, you can always just look at RIPE Labs, and we will publish most or all of our researches there. So I'm hoping that I was more or less coherent and you could follow. And if you have any questions, then by all means, contact us right here, right now, or on the usual channels. Thank you.
Thank you so much, Robert. That was incredible on the spot like that. Well done.
We should surprise you more often. That was it. That was a great tools update. Thanks.
Please don't.
Great. And this was actually the end of the RIPE MAT working group part of the program. So I'm going to hand over to Dave, who will take you through the next part of the session today. Thank you so much.
All right, can you hear me? No.
Yes.
Oh, you can. Okay, good. Thanks for joining us during your holiday, Robert. I think I take better holidays than you. This is the intellectual property rights statement to notify the following presenters if you have IPR claims regarding your work to disclose them in a timely fashion. So we're running about 10 minutes later than we thought we would, but that's good because we thought we would need an extra 10 minutes, so we should be able to fit this in time. These are the upcoming presentations that Miria and I arranged for the Measurement Analysis for Protocols Research Group. And Mark is up first, and Mark has asked me to run the slides for him, so I'm going to stop sharing this and start sharing that one. And Mark, are you there? Are you ready? I think I might have to unmute Mark. All right. Oh, no, I still see Mark is muted. There we go. And share, want preview, this guy. To view. All right. Take it away, Mark. We can't hear you. Can't hear you, Mark. I'm gonna stop sharing that for a second so I can go back and see. Mark, you're shown as unmuted in the participants list for me. Unmuted now. Try one more time. Yeah, can't hear you. Why don't you try disconnecting and reconnecting to the WebEx, and we'll switch to I think the next presentation in the meantime and come back to you. Does that make sense? I think he said okay. So let's see who. So who do we have up next? I think it's Jake. Jake, are you ready to go?
Yep, I can go.
Okay, let me make you the presenter. Hold on a sec. All right, Jake should be the presenter now. Take it away, Jake.
Okay, I will. All right, you can see my slides, I hope, and hear me?
Yep, we can see it.
Great. Hi, I'm Jake Holland. I work for Akamai. I'll be talking about some observations about latency and AQM that I started in about February. I'll go over a little bit of the background and goals behind what I was aiming for here. A couple of somewhat tentative conclusions that I have from the observations I've made, and just give a little pitch for, I'm mostly looking for a collaborator here, because I'm probably not going to do a whole lot more with this unless there's interest. But I think that just because it's not very actionable for us from where we're sitting as Akamai, but I think there's some worthwhile stuff in this data that could bear some improved analysis if anybody can be enticed into hooking up with me. I put a bunch of stuff in the backup slides also, so if there's more you want to know, take a look through those. This is we enabled ECN in February. And so we started looking at what we can see now that ECN is enabled. In some sense, I'm using observation of a CE mark as a proxy for existence of an AQM. I know that's a lower bound. Many AQMs do not do marking, but I nonetheless did a little bit of comparing between AQM and not within the same ISPs. And there were a few questions I wanted to get at first, which were how much are we seeing ECN usage and utilization? And the key one, which we did consider possibly actionable, was whether home router solutions can really address the problem or not. We're looking for whether we can get it down to a reliable 45 milliseconds to support end-to-end gaming. And for that reason, this is not really, I'll get into what I was looking at there when I get to that bit of it, but just put a pin in that. And my time to work on this was pretty limited, but so there might be some interesting yet unaddressed questions. So my first conclusion is that CE marking is not very prevalent. I'm seeing now about 0.3% prevalence. Last March, when after most of the shutdowns had begun, but before I had done a lot, also after we started being able to see the data, it was closer to 0.02%. I think we're probably seeing some ISP managed adoption. I'll go over a little bit why I think that. This was partially inspired by a prior talk. There's links in the slides. This is Apple's talk from a few years ago. But we're measuring from the server side, and we're basically looking only at the downstream. And I organized it by ASN instead of by country, because it seemed more meaningful after kind of looking at it. If you follow the slides, you'll see that it had a big observation in Argentina, but that was later discovered to be not relevant. So I was looking to see if I could replicate this, by the way, and I couldn't really. And I think part of this is because we're getting a different view on the marking, because when you're the client trying to download something, then when you get a better chance to see if there was any congestion ever to that client than we do from the server side, because we only will see congestion some of the time, especially if we are not actually inducing congestion, which often we don't. So here's a chart. What we're looking at here is the proportion of the clients that ever asked for ECN that actually saw CE marks, and sorted by ASN. And then the size of the ASN corresponds to the size of the data point. So this is just the top 35 or so ASNs, and you can see that it drops off quite quickly. There's a few ASNs that seem to have deployed something clearly managed by the ASNs that are sort of up in the, or by the ISP that's, up in the 80, 90 percentile percent of clients who ask for ECN do sometimes see marks during a day. But it drops off pretty quickly. There's a sort of middle ground here. So, here at 3% or so, it's still quite a bit, 10 times higher than the global typical count. So I'm not totally sure what to make of this, but my guesses are written here on the slide. I think that, for these larger ISPs that are seeing, 7% of paths or of client IPs do sometimes see mark, because it's quite a lot more people than you might otherwise guess. The smaller ones, so the largest dot on this chart is 103K client IPs in the ASN, and the smallest is 510. So some of these tiny ones are really pretty small. There's another filter I didn't mention here. This also is a little bit covered in the backup slides. There's I'm filtering for ISPs that had at least 100 clients that ever asked for ECN. So even in the 500 IPs, we have at least 100 clients that sometimes ask for ECN. But so the 3% that you're seeing here could be as low as 3 for a very small, 3 individuals for a very small IP. So I don't think that's particularly indicative of anything. It also should be noted that what we can see is a lower bound. So these are connections that or client IPs that actually on some of their connections did see CE marking. So there's the July line and the March line. You can see that between March and July, it increased quite a bit, and that we get a lot more in the way of large ISPs that have done something. However, that said, it remains quite small overall. This also does not represent most of the CE marking paths on the internet. These are the top ISPs that seem to be doing something with it. But if you look at the top 100, so that it continues down to a smaller long tail here, but out of the top 100 of the 800 or 1,000 ISPs that pass the filters, that only represents 1/40th of the CE marking paths on the internet. So so I'm concluding that most CE paths on the internet are not ISP managed. Most of them are probably these home router kind of deployments that are widely available. But of the ones that are ISP managed, there's not that many, but they seem to be growing somewhat. The reason I'm distinguishing between ISP managed and not is because we were interested in the question of whether a home router deployment would be able to address the latency issue mostly, or whether it really would need something done by the ISP. And my tentative conclusion here is that it probably needs something done by the ISP. It's not good enough to do it in home routers predominantly. So what I'm looking at here is the samples that I'll be presenting are all just the SYN to the SYN-ACK to the ACK. So this is just a snapshot, one per connection. That's right when the connection opens. And I'm not saying anything about the home router's AQM impact on self-congestion during an active TCP flow. I'm looking for mostly like what you would see in a gaming scenario where you've got a lot of chatty back and forth, but not a great deal of bandwidth. And I took the TCP handshake as a decent proxy for this kind of measurement. And what I'm seeing is that CE marking paths still experience a pretty high latency variation according to the ASN that they're in. That is different depending on which ASN they're in. Where did my? So the charts I'm showing are for 1 day of data. I was doing 1 day at a time, just partly because of the way it's partitioned for my access. This covers. I've done this separately on a few different days, but not in a really consistent and organized way. So I just sort of did spot checks for consistency between days and kind of qualitative judgment of the done any like putting the days together to make good sense out of them. So I picked 2 particular ASNs to go over. These are chosen to be just sort of from the kind of leading edge and from the middle of the pack of the ASNs I had available. And also I wanted to give a shout out to the presentation also a couple of years ago about, I think it got me thinking about the right way to do that. Links there, that's a good one. So what I filtered for, I was looking for the, trying to isolate the effect on the access network. So as a CDN that has a large edge deployment, we were looking for like what is the impact that we cannot address by sort of mapping better or having more edge servers out there. Like what are we going to be seeing even if we do everything perfect on the server side? And I'm looking for the latency span. So I took only client IPs where I had at least 50 samples from the same data center to the same client IP in the same day. And I topped it out at 300 samples from any data center to the client IP. And the reason for that is to exclude carrier grade NATs and VPNs, which have you know, a very wide variety of paths. And again, in the backup slides, there's a chart that shows like why I think 300 is about the right cut. And all of the client IPs that made it into the end had at least one RTT sample that was 20 milliseconds or below. So after these filters, I get about 5.3 billion samples across 31 million client IPs. There's 11 million of these client IPs that ever negotiated ECN, and 33,000 of them that ever saw markings. So the data, also one other point to make is that I talk about client IPs because that's kind of an easier way to think about it, but each of the points in the charts is actually looking at a data center to client IP pair. So there might be multiple different data centers that talk to the same client IP, but those would show up as separate points in the chart. But the same client IP cannot appear more than 6 times, and probably not more than 5, because it would not have passed the filters if it did that. So the charts say pairs, but I'll be talking probably about client IPs instead. So the quote good ISP, this is kind of what I see. So there's 8 different CDFs here essentially. And what they are is the solid line is the 50th percentile of the client IP's span, of the latency span they observed over the day. So however many samples they had, you know, we've got a client IP that's was in the middle here, and their 50th percentile was had an RTT that was, you know, at this value. And then we have the same chart for the 75th percentile, the 91st percentile, and the 98th percentile. So as I said, each client IP, each of the points on this chart has at least 50 samples. So we've thrown out at least one. And at least the top outlier. But these 98 percentiles values of the latency span for the client IP, then each of those clients would represent some point on this chart. And another point worth noting is that the same client might have, you know, a 98th percentile up here and a 91st percentile down here. They're not necessarily the same client all the way across. The only real restriction would be that within the client, it's monotonic. But so given that, what we've got is the green charts are the baseline. So that's all of the data points within that ASN, and the blue ones are just the CE marking paths. Whether or not those mark, any client IP that ever in the day saw a CE mark is included in the blue chart. So you can see that this is what, about 0.2% ish of the IPs that were in the filter. So these are all within the same ASN. And one interesting thing to note is that in this case, it looks like some of the CE marked, some of the CE marking paths actually had a worse 98th percentile than the overall paths. I'm not sure if that's selection bias or if it's an artifact from running an AQM. But this represents an ISP where we think there's not an ISP managed marking deployment. These are the kinds of numbers I have for this. I have probably 1,500 of these charts, I guess. So I just picked one out to be illustrative here. Per day that I run. So a middle ISP is just chosen from the middle of the pack according to their 91st and 98th percentile. And this is about what we see there, where it's the same thing, but the pink line is CE marking and the orange line is the overall latency spans that we see. And the conclusion comes from, if you just look at the overall values of the good ISP versus the middle ISP, it's pretty clear that this is, being in the good ISP is dramatically better than doing CE marking in the middle ISP. So this is pretty typical. It's not universal. And again, I have another chart in the backup slides of a different middle ISP where it was a better value for marking CE, for CE marking paths. But this is sort of the evidence that I'm using to conclude that we cannot solve the latency problem by doing home router deployments. So for, where do I want to take this next? I feel like there's a lot of unexplored questions in this data, but it's, I had to tell my corporate overlords here that I could easily spend 6 months or a year digging on this and come out with no concrete recommendations for what we should actually do in our network. And so I'm basically dropping this unless somebody reaches out to me and is interested in developing this further. So yeah, do that if you think it should be developed further and you have some ideas on how to do so. Just wanted to get that out there and let people know kind of what things we're seeing. And I will take questions if there are any.
All right, thanks, Jake. Yeah, there are a few. We've got 3 questions for you that I'm going to ask on the questioner's behalf. Bob Briscoe first asked the question. Back on your slide 5, you were showing CE marking prevalence, and Bob asked, is there any check in your work to look to determine if it's real ECN marking and not field mingling?
I did do some spot checks. There's a few points of evidence that I have. I don't. It's not great evidence. I looked for any CE or ECN markings on paths that did not negotiate CE or ECN markings, and I never saw any of those over the span that I looked for them.
Okay.
I'm not sure that there's. I'm not sure that it never happens. Obviously, it these things could happen, and now that I've mentioned it, maybe they'll start happening. Who knows? But nobody was doing this as far as I could ever see during the time I was looking at this. I don't have, if you're talking about the kinds of traffic that was reported previously where ECN marks were happening on every packet or something. No, that also was definitely not happening. Most of the time, what we're seeing is a small number of flows ever get CE marked, even in the even on the paths that are doing highly prevalent CE markings. But we did not observe a lot in the way of we're relying on the client heuristics that Apple talked about for when they see a problem where like every packet is marked, then they will sort of cut off the negotiation of ECN. We're not doing that actively on the server side because we know it's out there on the client. We're not behaving differently from other servers, and it's also like way harder to do that from the server side, as far as I could tell.
Okay. Let's jump to the other two questions. Jay Ignacio asks simply, are the ECN observations all on IPv4, or do they also include v6?
This includes v6 as well.
Okay. And then the third question was also from Bob, and he's asking, could increase in congestion experience be due more to congestion over an existing ECN node rather than an ISP having newly deployed ECN?
This is possible. It's a little hard to tell from where I'm standing. You know, there were more samples on the day I chose in July than in March. Part of this can be attributed to the normal growth that we see in traffic over time. But you know, in both cases, the days I picked here were Sundays since COVID started. You know, it's not. Yeah, I don't have a solid yes or no on that, but I'm rating it relatively unlikely, but not with great evidence to do so. So I would say if I had contrary evidence, then I would, you know, I would change my mind on that.
Okay. Okay. Thanks, Jake. So just to reiterate, Jake is saying, you know, if there's a collaborator that's interested, both he and I have worked on some of this stuff in the past. Maybe it's something we can do in MAPRG in the hackathon. And all right, what I'd like to do now is I'm going to switch to making myself the presenter again, and then we're going to check in with Mark McFadden and see if we can hear him, because we can just squeeze that.
Can you hear me?
Yes, we can. Very good. So I'm going to bring up Mark's slides, and we'll run through that. Let's see. There we go. I'm going to go view slideshow. Okay, take it away, Mark.
All right, thanks, Dave. This will be quick. This is completely different from the other presentations that we've had today. This has been motivated by some work that is going on. Oh, maybe we could go back one slide here.
Yeah, sorry about that.
That's okay. Anyway, there we go.
I'm sorry, you want this?
That one right there. So thanks. So this has been motivated by some work that's going on in the IAB, and it was a sort of thought experiment originally. A very old RFC 3552, gives guidance to authors in terms of crafting language for security considerations, but that is actually pretty old if you think about it. And so what we thought was, what if you actually examined the RFC since 2003, looked at the security consideration sections, and tried to determine whether or not there were fundamental and crucial changes to the threat model for the internet, and also significant changes to the way that people were writing the security consideration section. And this isn't just a sort of piece of independent research. The idea was really to inform some of the other work that's going on in the IAB. So next slide, Dave. Yeah, so the IAB has already talked about potential revision to 3552. The IAB currently has a piece of work underway right now called Cleverly Enough Model T, that's talking about changes to the threat model that are that's in RFC 3552, and really the body of work since RFC 3552 is actually fairly substantial, since we're in the neighborhood now of having 5,500 more RFCs to look at. So next slide. Thanks. There's two things going on here. First of all, I published a draft that actually talked about a possible methodology for doing research on the security considerations text that are in RFCs. And it really proposes a pair of components. One is a quantitative component, and more about that later. The quantitative component is really a textual analysis of the words that are in the RFCs, and then a qualitative analysis. And so what the draft does, what the proposed piece of research does, is propose this methodology. And what you'll see in a moment is that this proposed methodology, one part of it, we've done an experiment on. So the next slide, please, Dave. So what the methodology is in search of is comments for improvement. Basically, except for an experiment that I'll report on in a minute, the actual methodology hasn't been implemented yet. There's no one who's actually executed it, although there have been volunteers who've stepped up to the plate and said they'd be interested in doing it. Things I wanted to take some time on here is to report on a quantitative experiment that we've done. And the draft also reports on that quantitative experiment, so you can find out more details in the draft. And next slide. Perfect. So what my co-author did, and we worked on in the summer and fall of last year, is that we did a word-by-word textual analysis of the security considerations of all the RFCs since 2003. And the thought was here, the hypothesis was, would you detect changes in the words that are actually being used to indicate the threats and the threat models? I mean, has it, if you look over the period of 17 years, has that changed? And would you find patterns that indicate that some terms have become more important to protocol designers by virtue of appearing more often in RFC text? And then one of the things that this last bullet on this slide, my co-author was exceptionally interested in, was taking a look at whether or not security and large-scale security incidents on the public internet had changed the way that that protocol designers had written the security considerations of their documents. The idea was, do events in the real world on the public internet affect the way that protocol designers do their work and express that work through the security considerations sections of these documents? So this experiment we did perform. And so next slide, Dan. My co-author actually executed a experiment that was consistent with the quantitative part of what's in the draft, the quantitative methodology. And basically what this does is it uses a set of Python scripts to extract the security considerations document out of the texts of all of the RFCs, and then parse each one of them and get word frequency counts for each. It's a little more complicated than that. There, for instance, it supports stop words. We omit words, and you'll see in a second that we conducted a second experiment to see what the indication of normative words were in security considerations documents. And I'll report on that in a second. So next slide. So the parser that we used was basically an open source parser. It removed all non-textual material, and it removed what we call stop words, words that are either words like a, and, those sorts of things, or other words that wouldn't, in our judgment, be related to the protocol itself. It also removed some other materials, for instance, RFC references and anchor URLs and so forth. And then it took all of that text and it parsed it into files by year. So the RFC was actually parsed year by year so that we could actually have sort of a time series of what the RFCs looked like, or the security consideration sections of the RFCs. And then for each one of those years, it built a frequency list of all the words that weren't in the designated list of stop words. So next slide. So The result of that experiment are a pair of files that go back to 2003, and one is a simple frequency, a word frequency count file for the number of times a particular word appears in a security consideration section. And one of the things we were looking for, of course, was, well, do new words start to appear as we move forward in the years or in response to particular attacks? And a second thing we did was to actually do an RFC count of how many security sections actually referred back to previous RFCs, what those RFCs were, and what the quantitative data was for that. So Dave, could I go to the next slide? So here are some examples, just so that you can see. This is actually taken directly from the internet draft. You can see some word. I won't read these out, but you can see some words that are fairly recent in 2019 RFCs. And then you can go back, and what I did for the purposes of this is to just step back 5 years each time. And you can see that one of the things that we observed was that actually both the distribution of the word counts and the words themselves frankly didn't change very much over the space of 17 years. And so that's interesting to us. I think that's interesting input to the Model T effort, for instance. It shows that people who are drafting RFCs are tending to use the same words despite the fact that the internet is evolving significantly. Again, there's more details in the internet draft, but this gives you a feel for what the top 10 word counts are in 4 sample years separated by 5 years. So next slide. One of the things we did that we sort of discovered was that there were many security sections that had normative language in them. And so I have 2 slides about this. First of all, if you remove the normative language, you come up with different top 10 lists. But one of the things you'll see here is that, once again, the words that are used between 2019 and 2004, frankly, don't change very much. And so what we're seeing is no reflection in the security consideration sections that is apparent by just doing a quantitative analysis of changes in the internet's threat model. And so one more slide. A couple results here. This slide may or may not be interesting, but we took a look at what the most common words were over the entire period of 17 years. That's in the first bullet there. And then over the same 17 years, here's a list of, in order of their frequency, what the 75 most frequent words are. We compared this then to the by year one, and this is kind of how we reach our conclusion that not much has changed in security consideration sections. And again, the results are in Appendix B of the internet draft. One more slide, Dan. And so here are some conclusions we drew. And I've already talked about them, so I won't, in the interest of time, bash this too much, but there really isn't much in the way of major changes if you're just doing word counts of the security consideration sections and actually look at that. That's in the draft proposes that you also do a qualitative analysis, and my co-author and I have not done that yet. It turns out that the word may appears more often than any other normative language in security consideration sections. We found that to be extraordinary. That the word may instead of must appears much more often in security consideration sections, and so that also is input to the IAB and input to other conversations about the internet threat model. And my last slide is just contact details, Dave. I'm happy to, first of all, have comments. Second of all, if anyone wants to talk about helping with the qualitative analysis of the data, happy to talk about that as well. Thanks, Dave.
Okay, thanks, Mark. Nina, did you see any questions in there? If not, I just have one. I love the idea of using the artifact that is the RFCs as a way to determine whether the engineering is moving with the real internet. Was there any real life internet phenomenon that you could correlate with the change in either quantity of words or just the quantity of the security considerations itself? I mean, you'd think you'd see evidence of the IAB or the IETF's policy changes even, huh?
So we looked at one particular case. This is mostly an anecdotal story, but we looked at the Dynattack, and we thought that certain changes to certain maintenance for TCP, we would have seen changes to the wording there, and we didn't. And we also looked at the latency issue, right? So for instance, Dave, if we look at, as an example, the Dynattack, one of the things we said was, well, we wouldn't start to see changes in the RFCs until about a year, 18 months later because of the publication, the pace of publication, right? But when we looked at that particular example, we didn't see much in the way of change. And we actually went back and looked at, we targeted particular series of RFCs. For instance, we went to a IETF area and then limited the examination to just, for instance, the internet area. And the results were pretty much the same. So, and I see in the chat room that Bob suggests that, you know, privacy should have been appearing more. And I agree with you, Bob, but it simply doesn't show up when you do the word count. And the word pervasive surprisingly appears in very few RFCs, even after the IAB statement on pervasive monitoring. So while we have a very, very strong statement from the IAB about pervasive monitoring, we actually don't see those words showing up in the RFCs afterwards.
All right, thank you. We're going to have to move on because we have just enough time to get the rest of the presentations in. So we're going to switch to Philip Brun next. I'm going to make you the presenter, Philip. And let's see, Philip, let's make sure you're unmuted.
Yeah, hi.
Okay, you're ready to go.
Yeah, so I'm Philip and I'm working for Ericsson. I want to tell you something about the behavior of TCP cubic that we have discovered in the context of my master thesis when doing measurements with cubic connections on mobile radio networks. So here you can see our measurement setup in the middle. We have deployed an HTTP server that is directly connected to the core of a mobile radio network and an HTTP client that connects to the radio access network through an LTE modem. The host here runs TCP cubic in default settings, and the round-trip time between server and client is between 18.5 and 30 milliseconds. And last of all, the radio link here can be seen as ideal in terms of a stable signal quality and no interference or cross traffic. So then taking this measurement setup and doing file downloads, we measured the total transfer time that also includes the time for the connection setup, etc., and calculated the file throughput as file size divided by transfer time. When we then plotted the empirical CDF for two different file sizes, we were actually surprised to see that the file throughput shows such a significant variance. So for example, for a 5 megabyte file, we have samples between 30 megabit per second and 50 megabit per second. So part of this is due to the current Linux implementation, and the fact that a smaller file seems to show a larger variance compared to a bigger file then led us to the conclusion that this might have something to do with the slow start. So then TCP cubic uses a hybrid slow start scheme called high start. So the window growth function is actually the same as in TCP Reno, but high start has two mechanisms to find a suitable exit point. So an exit point before we lose any packets. One of these mechanisms looks at the ACK train length, so the length and time of back-to-back ACKs that return to the sender. In our measurement, this actually never triggers, so we don't discuss this here. So then the second mechanism tries to detect the delay increase. So if the current round trip time exceeds the minimum round trip time by a value of theta, this then indicates congestion at the bottleneck link. So here the minimum round trip time is defined as the overall minimum round trip time that we have seen throughout the connection. And the current round trip time is defined on a per round basis. So the current round trip time is always the smallest round trip time sample from the first 8x of a round. I have summarized the delay increase condition down here, and the value of theta is actually defined as the minimum round trip time divided by 8, but is clamped between the values of 4 and 16. So since in our measurements the round trip time is small, theta actually always takes the value of 4. So then going back to this condition here, we can actually identify two reasons why this condition can become true. So either we already have found our minimum round trip time, and then the current round trip time increases, making this condition true, or we are outside of the sampling phase of a round, so beyond the first 8x of a round. So then the current round trip time is fixed, but the minimum round trip, but we could find a new minimum round trip time when the round trip time drops. So these are two separate reasons why this condition can become true. Since this is a little detailed, I want to give you an example and walk you through one example. So I want to walk you through one example for each of them. So here I have plotted the round trip time samples that correspond to different packets. And so for the first round, and here I have to say that the definition of a round from the high start point of view actually contains a bug. So high start considers the first 11 packets to belong to the first round instead of the first 10 packets. But actually what's the case is, since the initial window size is 10, the sender sends 10 packets in the first round, not 11. But let's stick with this for this example. So first of all, we have to find the minimum round trip time plus theta, so the threshold value that we compare the current round trip time against. And then we find our current round trip time as the minimum round trip time during the sampling phase, which is here shown in gray. So as long as we are as long as the dashed line is then above the solid line, we continue and go for another round. Each time we go for another round, we then reset the current round trip time. And then again, we find our threshold, which then here drops on the 31st packet. And we find our current round trip time, which is this time 20. So again, the dashed line is above the solid line. So we go so we again reset the current round trip time then and go for the third round. So this time we've already found our minimum round trip time. So the threshold here stays constant. But what happens now is that the current round trip time increases from a value of 20 to 22, which then makes this condition to become true. So then we keep on sampling, but do not find any other smaller sample. And we exit the slow start at the first egg after the sampling phase. So this then results in a congestion window at the exit point of 51. This in the example for the second reason is actually pretty similar. So in the first round, nothing else happens. In the second round, we again see the drop on the 31st packet. But this time, the round trip time of the 15th packet is higher than before. So now the current round trip time is 22 instead of 20, which then makes the drop on the 31st packet to force this condition to become true. And therefore, we leave the slow start immediately instead of going for the next round and leaving up here. So this time, the congestion window at the exit point is only 40. So now we have understood these two reasons, and we wanted to know, okay, how likely are these two reasons? So therefore, we did another experiment and actually figured out that the probability that we leave the high start due to an increasing round trip time, which is actually how the delay increase mechanism is supposed to work, only happens in 30% of the cases. But in 70% of the cases, we leave the high start when the round trip time decreased. So we actually left the high start when we set a new minimum round trip time. So now you might ask, how can this even happen that the round trip time drops in the middle of the connection? To understand this, I have to tell you something about the uplink scheduling in radio access networks. So in a mobile radio network, the radio access network actually controls all the transmissions, so also the uplink transmissions. So the modem needs uplink resources in order to transmit its data, or in this case, the X. So then there are two cases. So either the modem already has some uplink resources, then it can just piggyback a buffer status report onto the next data transmission, telling the radio access network that it needs more resources to transmit the rest of its buffers. So the rest of the data that it's still in the buffer. If the modem does not have any valid uplink grant, it has to rely on a 1-bit scheduling request that is sent in the uplink control channel. So to understand this, look at this example here on the right. So in the first round, the server will send 10 packets to the client, and the client will then generate 10x and send them to the modem. Consider the modem to be idle from a transmission point of view. So then the modem has to queue these 10x and wait for the next opportunity to send a scheduling request. After some time, the modem, the radio access network will then respond with a small amount of, with a scheduling grant that grants a small amount of resources, since it cannot know how much data the modem has in its buffer because the scheduling request is only a 1-bit information. The modem can then fit, for example, 2x and piggyback a buffer status report telling the radio access network it still has 8x in its buffer. So the first 2x are then forwarded to the server, and the radio access network will then grant send a sufficiently large grant in order to, so the modem can then in the next step send the rest of its buffer. So even though the 10 packets arrived at the client at the same time and the client generated the X at the same time, the X will arrive at so the X will return to the server at different points in time, and therefore the packets can have different round trip times. Another reason for the round trip time variance is also that the MAC layer has some periodicities. So when you look at this graph here, this time I've plotted the mean round trip time of individual packets. And by looking at the first 10 packets here, you can precisely see what I just explained. So the first 2 packets have a smaller round trip time, and then the round trip time ramps up by about 8 milliseconds on the third packet. So then this kind of scheduling principles also lead to the fact that the first 2 X of the third round are then transmitted together with the last X of the second round. So this means that these 2 X here do not have to wait for any scheduling grant, which could be triggered by either a scheduling request or a buffer status report. So they can just hop onto the transmission of these X. This then causes the round trip time to drop so significantly. And as we have seen in the previous examples, this then in many cases leads to a false positive detection of network congestion and an too early exit point. So at this point, the connection is still far from the maximum throughput. So then in the end, these MAC layer effects dominate the behavior and the performance of TCP cubic. So to conclude, so we have seen that cubic connections can see a significant variance in the file throughput, which is due to the high start that it usually, or in many cases, fails to find a suitable exit point due to the latency variance of LTE. As I said earlier, there can be made a couple of improvements. So on the one hand, the bug that the high start reset was done 1 packet too late, so that the first round contained the first 11 packets instead of the first 10 packets. We actually fixed this in our version of the kernel. And then there was also, our research also led to a different kernel patch that now allows every round trip time sample to reduce the current round trip time. So this means that we do not exit in the current round when we find a new minimum round trip time. So taking both of these together, we actually redid our measurements and found that for a 5 megabyte file, the throughput increased by about 15.7%. And what you can also see by the graph here is that the portion of samples that is close to the mean increased from about 55% to about 85%. So the jitter, the overall jitter was reduced, even though still have our strong outliers. So this is because there's still some effects that are not compensated by either the bug fix or the kernel patch. So since HiStart still does not consider the round-trip time variance, it may still not be well suited for mobile radio networks. And in the end, it's important to say that even though we conducted our trials with LTE, we presume that the same effects will also happen on 5G, since there we use the same kind of uplink scheduling principles. This is actually it.
All right, thanks, Philip.
I'm willing to answer questions now, or you can also send us an email later. So either me or my colleague Maciek, who worked with me on this.
All right, Philip, thank you so much. There's been a little bit of a lively discussion about HiStart in the chat session, and I'll suggest that those folks do what you just suggested, take it offline with you by email, or you can use the MAPRG mailing list as well. For instance, Bob Briscoe commented that HiStart is on by default in Linux Cubic. But according to a mini survey, he says he did of 4 to 5 CDNs about a year and a half ago. For instance, Google, Microsoft, and Apple, all but one had disabled HiStart. Do you have a comment, Phil, before we wrap up?
No, I don't. I just,
okay.
As we saw it, it really can behave badly when used on mobile radio networks. So.
Okay. Thanks. So in the interest of time, because we just have 25 minutes for 25 minutes of presentations left, we're going to switch to Mike Kosek being the presenter. And let me do that by finding Mike in the participants lists here. And we have a little bit of, as Mike gets set up, I'm going to paste in the chat right now a link to an Etherpad that Miria, my co-chair, who's on top of things better than I am, reminded me we're supposed to be maintaining what are the blue sheets, where basically you just sign your name and your organization and to say you were at the meeting. So it'd be a big help to us if you would visit that URL. I just posted there, the Etherpad MAPRG URL, and just add your name and affiliation there. So we get a list that approximates I saw about 74 participants on today, and we've got 56 right now. So in the next half hour, if you could sign that would be great, just like you would if we were at a real IETF meeting. Mike, I'm going to hand it over to you. You're ready to go.
All right, thank you, Dave. So this is a quick recap on our work of TCP conformance, which has been presented at PAM in March of this year. So TCP has been analyzed in the past decades. However, every study focused on different aspects of TCP and TCP extensions. And our question was, okay, how is the conformance to the minimum requirements? So the basic requirements, which are phrased by the must keywords in the RFCs. And for this, we chose an active scanning approach. We did controlled testbed environment measurements, first of all. We followed up with a large-scale measurement campaign. And for this, we used the tracebox approach to also detect middlebox interference with these minimum requirements here. So for our test cases, we looked at the RC 793 BIS, the draft 14 version. And we looked at different aspects. So we checked if the checksums are correctly validated, if options which are unknown are correctly ignored, if the MSS which are stated are the RC stated defaults, if the effective send MSS is honored, if reserved flags are ignored and zeros, and if the urgent pointer could be processed segments of arbitrary lengths. So with these test cases, we started out, and this is something we could, of course, only be observed on the wire. So there are a lot of more requirements in the RC draft, and we started with this because they, low-hanging fruit, I would say. First of all, we did some controlled testbed measurements. What we see here is that only Linux and lightweight IP showed full conformance to our test cases. When we look at Windows 10, then we see that the MSS default stated in the RC are used as a lower bound. So you cannot actually in the three-way handshake use something lower than it's stated in the IRC. For macOS, the 1024 bytes are used as a default regardless of the IP version. So this falls short of the IPv6 and exceeds the IPv4 defaults. On micro IP, we actually observed some crashes, and this was done on urgent pointer data, which was pointing beyond the segment size. And we issued a pull request for this. This was especially interesting as ContigiOS and Contigi-NG OS are also vulnerable from this issue. And this pull request got merged and is fixed now. For C-star, we saw that the host OS is supported of offloaded checksum features is not verified. We reported this issue, however, to this date, we did not get any response from this. All right, for our large-scale measurement campaign, we looked at different target hosts. From the HTTP archive, we sampled CDN targets. There are 28K unique targets housed. We took around 476,000 unique target hosts from the Alexa top 1 million list. And on Census, which provides internet-wide port scans, we took around 3.2 million target hosts. So let me start with the notation here. In our 3 columns, we see the 3 data sets, and in each sub-column, we see the different results which are presented as a percentage. So for UNK sub-column here, this is unknown. These are not clearly determinable results. This can have multiple issues. For example, if a pre-test was successful, but the actual test of the feature we wanted to check, we did not get a response to our SYN packet. Then we have F-target, which shows non-conformities raised by the targets, and failure path shows non-conformities raised by middle boxes. Okay, digging right in. First of all, we have the checksum test. We did this in 2 ways. First of all, we chose a random incorrect checksum, and we also did a test with 0 checksum. And for checksum, we saw that the CDN shows the lowest failure rates overall and actually no on-path modifications, which is quite good news. However, Alexa and Census each show around 3% target failure. So in around 3% of the targets, they did not validate the checksum and responded to our false checksum package. Next of all, we have option unknown. And so no single S really stands out here, but we observed that the highest failure rates are within ISP networks. And this is exactly the same behavior as we saw in the MSS missing test. So for MSS missing, we saw around 0.4% failure on the path of the census data set. And these are also primarily located in ISP networks. And digging down on this, we saw that the MSS is inserted here, and this is most likely due to the PPPoE encapsulation done by access routers. Next up, we have reserved flags, and we see up to 1.8% target failure on census here. So they actually did not respond to our probing packets at all. And this is really bad news for extensibility, as using these flags really doesn't provide any connection to these targets at all. However, when looking at the RC, we see that ignoring and zeroing the reserve flags is actually no formal must requirement. So for this, we propose to add this as a formal must requirement within the RC 793 BIS version. Lastly, we have the urgent pointer, and the urgent pointer shows the overall highest failure rates with up to 7.3% failure on the census data set. And these census fails are primarily located in ISP networks again, and around 99% of these failures are just silently discarded the data. So no connection is possible using the urgent pointer with these hosts. The RC states for the urgent pointer that the usage is actually discouraged, but the implementation is still mandatory, and it might be an idea here to remove this mandatory implementation requirement to reflect its deprecation in the RFCs. All right, so that's for our quick recap. Please have a look at our paper if you're interested. There are a lot of more test cases and more details in there. We also released our data set, and we released our code. So our tool called TCP-Rec is on GitHub. Feel free to contribute, feel free to share your results. I'm happy to progress this further. Thank you.
Thanks, Mike. And we have a couple of minutes for questions. The first one that was in the chat was Jay Ignacio asked, how did you determine, this was during your results presentation, for instance, the results slide 2, how did you determine the middle box errors instead of targets?
Yes, let me just bring up my backup slide here in our methodology. So we used the tracebox approach where we encoded the TTL in multiple fields and just sent out multiple increasing TTL probes and listen for the ICMP time exceeded messages. And we did this test case specific. So for example, if we wanted to test if on a path the TCP checksum is corrected, then we would get a reply with a corrected checksum with this approach. And then we could say, okay, this was a failure that actually happened on the path and not on the target. And we did this for all of our test cases. So this was a lot of handcrafting. There's no general approach here besides the tracebox approach, which generally can give you a hint if there is a middle box or not.
All right. Yeah, thanks, Mike. I don't see any other questions there, and we're just on time. So, and Jay Ignacio says thanks. So I'm going to switch the presentation, switch to the presenter being Stephen Strohs for the last presentation of the session. Stephen, you should be the presenter now.
All right. There we go.
One last reminder, please visit that URL that I posted in the chat to sign up for the Blue Sheets. We've got about, I think, 60% of the folks have signed up so far. I'm sorry, go ahead, Stephen.
All right, thanks, Dave. This is a summary talk of work that we've presented already at TMA and at the NRW, and this covers the deboganization of 2A10/12. For a little bit of context, this was the first /12 allocated by the IANA to any of the registries in, at the time, I think 13 or nearly 13 years. Which is long enough for, router configurations to become stale and things for, to be baked into the routing system. So before we issued it to members, we wanted to light that up, get that announced out there, and generally try and do some checking to make sure that it wasn't packed with pollution, which is unlikely, but you don't until you measure. So the timeline for this was, we actually got the /12 back in late 2019, but in early 2020, the previous /12 was nearly done. We were imminently about to start allocating from 2A10/12, so we had about 1 week to advertise this and collect what we could. We announced 9 prefixes in total, the full /12, then 4/32s and 4/48s. Each of these were configured slightly differently in terms of whether they had a route object in the routing database or whether they had an RPKI ROA. And the 32s and the 48s all had a responsive target. So each of the 8 addresses in total would respond to ICMP echo requests. This has mostly already been covered in the TMA paper and the ANRW paper presented last week. So links to the papers and the videos for the papers, both there. If you want to go follow up on particular details. For the rest of this, I'm going to cover basically the summary version of what we found. The bulk of the TMA paper is basically traffic analysis. And the way that we kind of think about this is with the IPv4 space, you could listen to, for example, a /8 if you have a full /8 lying around. And depending on some of the behavior, you may be able to draw general conclusions about background noise to the IPv4 space. Like each v4/8 is going to be different in terms of what it attracts. But the v4 space is also small enough that you're going to see internet-wide, quote-unquote, scans. The v6 space is quite different. It's a bit more like taking a telescope and pointing at the sky, and simply observing what you see in that part of the sky, there may be something generalizable there, but it's more likely that you can report on what you saw in that corner. So that /12 is a lot of address space, but it's still a very small part of the V6 address space in total. So what we got is what we got, and I would be careful with drawing general conclusions around that. The part that's kind of a good start is the bulk of the traffic that we actually captured was our own traffic. We sent a lot of measurements into this space to the responsive targets from the RIPE Atlas platform. And so the vast majority, in my head, I'm thinking that looks like around about 90 to 95% of the traffic that we captured was generated by RIPE Atlas. So we can ignore that for most of the rest. The remaining traffic consists around 6.5 million captured packets, which if it was on an average, which it's not, it would be around about 10 packets per second, which is, at that point, nobody cares anymore. The traffic can be carved out in a couple of broad categories. The bulk of the TCP traffic was what looked like an orchestrated traceroute campaign to locate responsive, to do two things, to map out topology and then find anything that's responding in port 80. The UDP traffic was around about 50% DNS, and the bulk of the ICMP traffic was solicited echo requests to the addresses that we set up. So for each of those in turn, around about 5.5 million of the packets contained a TCP payload, and they were doing some kind of TCP traceroute, right? So trying to repeatedly reach the same target, but with an ever-increasing TTL until it eventually gives up. All of that traffic has the same basic characteristics, so like the same source port, no payload, send flag is set, nothing else is active in the packet. The MSS value is set as if it's configured for an IPv4 world. There's a couple of glitches like that. And most of this traffic in the activity graphs that are in the TMA paper arrived in a couple of short periods very near the start of the study. So like very soon after the full /12 was advertised, this TCP scanner lit up. My gut feeling is that whatever this thing is, I don't know who's running it really, whatever that thing is, it was never expecting to see address space that large, and something bugged out in whatever the platform was, and it started sending far too many packets into the space. And my gut feeling for that, the reason I have that gut feeling is that once we lit up the 32s and 48s, there were specific trace routes into those addresses, but at a much lower volume. So those lit up very quickly and then stopped very quickly, which was good. Basically, they bounce around in random addresses, though. There was a distinct port scanning operation from one origin to around about, sorry, I have target addresses in the next slide. Around 164,000 packets doing port scanning from one origin. And then like tens of thousands with a destination port 443 and an ACK flag set. I can't remember if they have payloads, but I figure something is either backscatter or is bouncing around looking for resets rather than synapse. And there's a lot of general noise that's otherwise uninteresting beyond that point. For the traceroute campaign, the addresses that campaign selected appear to be random bits filling the bottom 116 bits of each address. And the assertion there comes from like the campaign selects in total 261,000 targets spread across 261,000/64s. Like it's not trying to do anything smart with particular addresses inside a /64. It's just trying to get something, whether it's topology mapping or not. The remaining targets are pretty well distributed. This graph on the right is ranked like most popular /64 target and going down from there. But there's 133,000 targets, and this forms a very, very long tail where many of the addresses are targeted maybe once or twice. The top target on that list was targeted the most for the port scanning campaign from one origin. And the set of sources is again reasonably broad. Like there aren't there's not much evidence of sources doing things like address cycling within its own /64. Sources pop up and then vanish. The port numbers that were targeted are a little bit interesting, maybe. Like I've taken port 80 out of this plot because it would swamp everything with the traceroute campaign, and what's left is kind of broad. Like at some point, basically everything is attempted by something. There's a lot of noise. The most popular target is port 443. And then from there, it hits, and I'm going to go by memory here, 6379, which I think is Redis, 5222 is maybe XMPP, and I lose the track from there. There's quite a lot of traffic with a TCP port 0 set. But this is, aside from a general leaning towards the low numbers that the port scanning does, a lot of this is like randomized payloads and weird targets. The UDP traffic was much less interesting, I guess. There wasn't much of it. 50% of the UDP that we captured contained a DNS payload that looked like legitimate DNS. Like there were DNS queries for A and Quad A records for popular names like google.com or various CDN CNAMEs or whatever else. This one, we did actually approach the network operator, and they found the person who was running a DNS resolver, which was misconfigured and was sending these queries into our address space. So that one was in theory fixed, but we're no longer announcing that address space, so we can't verify that it was actually fixed. The ICMP traffic was largely solicited. This is again on the right, a ranking of the most popular targets, and the top 8 targets are the 8 basically reflect the 8 responsive targets that we created, and we requested the network operators send their traffic to. This graph is ignoring the RIPE Atlas traffic also. So most of the ICMP goes to where we asked people to send ICMP echo requests. The next most popular is 2A10 with all the zeros, which was unresponsive, but a lot of people selected that one rather than : 1. Maybe people truly are that lazy, I'm not sure. And there's a long tail of otherwise essentially randomized traffic targets again. A bunch of these in the remaining targets are like genuinely what appears to be randomized payloads with invalid ICMP types and codes and so forth. So a lot of that stuff is just weird, and it's the numbers at that point get so vanishingly small that we basically draw a line under it and declare it to be acceptable noise. Like there's nothing that we observe in this data that spooked us. There's nothing that we observe in this data that would make us say, okay, this particular slice of the address space we want to withhold from the membership, and that was part of the purpose of the study. We cover aspects of the routing state in both the TMA and the NRW papers, although not in a spectacular amount of detail. We wanted to make sure that first the space was basically routable, and then from there we used the RIPE Atlas measurement platform to ensure that it was actively reachable if we tried to get there. And in general, it was. We got about 99% hit rates on our pings and trace routes, which is basically typical, apart from a couple cases, including AS8881, which I think is Versatel in Germany. We got no responses to any of the targets on that one, and I think we inspected the PCAP data, and that one is inbound filtering. So we saw the echo requests at the targets, but the probes themselves never received the responses. And the other more interesting one maybe is AS3320, which is Deutsche Telekom, and then ASNs that appear to be routing via AS3320 could reach a subset of the targets. And for those ones, the probes were unable to reach the responsive addresses inside the prefixes that were configured to be the least routable. So the prefixes that had neither the route objects nor the RPKI ROA, which is kind of fine. Like those are the ones that we would expect to be less reachable, so that's completely okay. And on those ones, we didn't see the echo requests arriving at the at the route collector that was announcing the space. So for those ones, they are filtering the routes at, I guess, 3320. So our current status and where we are with this was a study in January. This is basically historic at this point. The RIPE Atlas data and the rest routing data is, of course, all public. The routing data in particular, you can also, it would be interesting to look at from other vantage points, such as route views or PCH data or whatever else. And now that some time has passed, we might be able to get to the point of actually releasing the captured data. It's something that we want to do, but it's trying to do that balance between how much of this is weird data that nobody cares about and how much of it is like identifiable data that tells us something. So we need to look at how we mask that data, or whether we strip payloads, or what we do with it to be cool. But 6 months have passed, so time is on our side. The address space.
Just Stephen, we just have about a minute left in the official time. I'm happy to go over, but I just wanted to let you know in case people have to leave.
Yep, sure. So I'm about done. So the 2A10/12 is now in use soon after we ended the study. So the week in January is on the left-hand side. Soon after we ended, that was issued to members, and then those prefixes started lighting up. The only reason that the numbers go up and to the right is that RISC continues to add new peers. So we have more peers simply listening to and receiving these announcements. And the address space that we allocated our 8s, 32s, and 48s from was put into quarantine because we did active measurements to it and we solicited traffic to it. That space is now out of quarantine. The standard is 6 months. So the space has now been reissued. And I haven't checked today, but it's likely to show up in the wild soon if it's been allocated to somebody. So there's a potential comparison there between the address space announced from our route collector system and the address space announced from somebody else, if somebody wants an interesting routing side study. And these are only my endnotes indicating what we did here. There isn't anything in this space that's entirely problematic. The routing and reachability seem to be good, and so we were completely happy going ahead and issuing that address space to our members. And that is my high-level summary of these two papers. So that's what I have. So I'm super happy to take questions.
All right, thanks so much, Stephen. I don't see anyone in the queue in the chat session, so I think we'll wrap it up. Thanks so much to you and all of the presenters for participating in our measurement community and bringing this interim meeting together. Let us know. I want to thank Brian and Nina for doing this experiment with us, this joint meeting. Let either them or us, Miria and I, know if you like the joint meeting and how you'd like us to meet in the future. And I want to especially thank Miria for encouraging presentations and helping curate the content because she did a lion's share of it this time again. Have a good day, folks.
All right, thank you.
Thanks, bye.
Bye-bye.